to the Drude model, right? This gives you the overall idea as to how plasmas respond to the electric fields. And again, above the plasma frequency, a plasma is completely transparent to an electric field. Below the plasma frequency, the plasma is completely reflective. That is, that it eventually will reflect all of the light out because there's no loss in the plasma, or the loss is so small that above the plasma frequency, the loss is very small, but the electrons can respond freely. So, sorry, below the plasma frequency, the loss is small. And so you get complete reflection, but again, you get a phase shift when you get that reflection, which the phase shift depends upon how deep the field penetrated into the plasma before it was reflected. But the overall field decays exponentially. The real reason I wanted to get to the plasma is that there's one other neat thing that happens. Neat and horrible. Which is that when we started all of this, and I've misplaced them, I wrote down relationships between the fields, the electric field, the magnetic field, and the propagation vector. And then said the solutions look like this. We looked at these solutions for transverse waves, where the electric field, magnetic field, and the propagation direction, sorry, electric, magnetic, and propagation were at right angles to one another, right? I didn't tell you that if the dielectric function is imaginary, then it's actually possible to have solutions in which the electric field and the propagation direction point along one another. You're going to have longitudinal waves. Right? Now, the extent to which they're longitudinal depends upon how much imaginary component you've got. In a plasma, the index of refract, or rather the conductivity is entirely imaginary, and therefore K has got a huge imaginary component. I wrote n squared there, right? But when we are below the plasma frequency, I got that right? Yeah. When the frequency is below the plasma frequency, n is going to be imaginary. It's okay? Not okay, tough, right? So we can have, let's say I've got a wave which is propagating in the z direction, right? And then I can ask, how can I satisfy Maxwell's equations under that situation? Unfortunately, I wrote these notes last year, and now I can't remember the justification for the equation that I'm about to write. So I'll make that an exercise for the students. But we end up with a relationship that looks like this. And yeah, good. Let's dot that into Z. And I end up with this. This goes away. I'm left with 4 pi sigma mu over C times the electric field plus epsilon mu, dot Z plus epsilon mu over C I've just got to satisfy that. That's the Z component of the electric field. So I don't have to rewrite that. I'll just do this. And that's easy to solve. Just separate values, separate variables, and integrate. And I end up with this. That the electric field in the Z direction looks like some E0 Z component, e to the t over tau, where tau is epsilon over 4 pi sigma. So there's a longitudinal component of the electric field for this wave that decays with time, and therefore decays with distance, that is permitted by Maxwell's equations because I had an imaginary component, the sigma, to the wave, right? So when we are at frequencies below the plasma frequency, I can have a wave incident on my surface, which is, you know, an oscillating, freely propagating wave. It passes into the surface, and I end up with components of the electric field along the surface and perpendicular to the surface, which decay with distance and time. Yeah.
Is there a missing negative sign, or is sigma?
Yes.
Sigma
I'll put it here. Thank you.
You have chalk on your face.
I have chalk everywhere.
I think the yellow chalk from last week is under the table.
It is.
Yes. But my knee is out, so I can't get it. But I brought a box of chalk.
Foxo chalk?
So chalk.
Yes.
Nice.
All right. Now to get where I was supposed to get in this class, because this was too much fun. So this really is something completely different. So we actually, maybe I should say, we only have a few more classes left. Yeah, I'm going to be missing it. And the things that I want to cover are fields from moving charges, and antennas, that as a result. Is that right?
I think it's antennae.
One N or two?
2.
Two.
But with an E instead of an S.
Yeah. Just put an S at the end of that. Antennae.
We're in America. Moving charges. Okay. Antenna. And waveguides.
How do you spell it?
This is messy. This is simple, but we could actually have a whole half a course just on waveguides. And the electrical engineers do, because waveguides and antennas, they'll make the whole course out of antennas and waveguides. So if you're really interested in antennas and waveguides, you should, and I'm actually not joking, you should go ahead and take Fields and Waves, the electrical engineering course. You know, I'm not even sure that they offer 2 anymore. So I'm going to say 1. Does anybody know? Electrical engineers? No electrical engineers here? No one wants to confess?
Where's the bird chirping when you need it?
Yeah, okay. So moving charges. Let me say something that is, well, I've probably done a lot of this, disturbing, all right? And it's something that I said earlier to you, but you just accepted it. Which was that if I have a charge that's moving along at some velocity, and I want to modulate the electric field over here, all right? Then where do you calculate the field is coming from? Right? Well, okay, the charge is here at this minute. You go out there and say the field must look like that, but the charge is moving. And what it turns out is that if I'm measuring the field at this point here and the charge is moving along, the field that that point actually sees at a particular time is the field from, I have to be careful about how I say it, and I'm going to screw this up first deliberately, right? Because nature isn't like this. It's the field as though the charge has just continued moving along. And it takes time, CT, to travel, for the signal to travel from here to here. Okay? In that time, the particle has moved from here to here. Right? The field that is detected over there points that way, not this way. Okay? The field that's detected out there is as though it's coming from where the particle will be when the signal arrives over there. Okay, yes.
Will that change under the effects of acceleration?
Oh, yes.
No.
Well, in fact, and this is the reasonable part, right? In fact, if, you know, at some point the charge is moving along like so, right? And then we say, okay, when this signal arrives here, what does it think the field is, right? It thinks the field is here. What if I stop the particle? There. It's going along. I stop the particle there. The signal that is seen over there is as though the particle kept on going, because it doesn't know yet that the particle has stopped. Okay? So for every object that's moving, there's a circle of radius CT around it, within which the motion of the particle out to a certain time is known, and outside of which the motion of the particle is not known, right? So if I were to make a sketch of what the electric field, let's say, looks like, let me say the particle should have gone here, right? And the time that it took for this signal from here to go out. So a signal was sent out, right? Then outside this, let me make it more extreme. Should be here, right? So the outside world actually thinks that the particle has arrived, that it's traveling there. And the signal that I see outside of this radius looks like that, as though it's coming from here. Okay? Inside the radius, it knows that the particle stopped. Maybe it stopped right here. So inside the radius, the field looks like this. And those fields have got to be connected to one another. And if I am remembering correctly, they connect with a discontinuity. Looks like that. So the field would have, thinks, if it's inside the CT radius, then it thinks it's here, but in fact, when we're outside, it sees it as coming from there. Okay? Now, the extent to which there's a discontinuity here depends upon the acceleration of the particle at the instant that it was stopped. Okay? You can't stop it instantaneously, and so as a result, this looks more like that. All right? Okay, so that's the idea, that inside of some radius CT, the position, the actual position of the particle up until something was changed is known, and the fields reflect, let's say, the present state of affairs. Well, actually that's not true. They reflect whatever was happening up until the change occurred. And outside, it's the state of affairs. If you took it where it was, what its velocity was, and you work out where the particle will be, it observes the field as though it's at the point where it was moving to. Yeah.
So you have the thing moving along, and the field that it makes is as if it keeps moving.
Yes.
And when you stop it,
The rest of the world doesn't know.
Yeah, a discontinuity of sorts moves out at CT.
Yes.
And that is the, okay.
Yes.
Just making sure I can sort this thing.
Okay. So the bottom line here, as far as doing a more legitimate calculation, then I should have brought my hands for this, okay? Than that, right? Is that there's some difference in time that we have to pay attention to. Where if I want to measure something out at distance, let's call this r prime, and let's call this position r, all right? I want to measure out to that distance. There's a time that's important here, which is the actual time minus, let's see, r minus r prime over c, and since it's a time, I'll make that. All right? This thing here is called the retarded time. It's behind it.
Neither of those R vectors have primes.
Oops. And it doesn't matter which. One of them has to be prime,
Right, could you put the?
because I made the absolute value of it. So we've got to make some correction for the time that it takes for things to get wherever it is that we're going to make our measurement. All right? And the fields that we measure reflect the state of affairs at that earlier time. Okay? So that's the key idea. And then what we're going to do is just guess a form for the potential and see whether it satisfies the wave equation, the full time and space wave equation. But this is the idea, as Brian said more succinctly than I did. These are 4 vectors, so I'm going to use some 4 vectors, but the details are, from my lecture point of view, are not so important. You can read Ohanian with or without in order to get the 4 vectors right. Okay, I'm going to talk about the idea, and unfortunately there's going to be quite a bit of formulas, and I'm probably going to make a mistake. Just give you the warning there.
So, before the next
I just
class,
want to give you the idea. Yeah.
before next class, should I stop by your office and ask you to bring your hands?
Yes.
Sure. So, wave equation. That is just 1 over c squared t squared and t squared in real time. All 4 terms, so I've got the electric potential in there as well. And that's got to be equal to 4 pi over c for current. Yeah. And we're going to take along for the ride. Oh, yeah, no, that's correct. Because this is what Ohanian does and Jackson, we need an additional condition when we're solving the wave equation for vector potential, which is the gauge that we're going to use. We're going to satisfy the Lorentz condition, which is d mu A mu equals 1 over c. Well, it's this equals 0, and I'll just write it out for you. That's the normal vector potential, the 3 vector potential. So separating it all out, we're going to say that that must apply. Okay. And now we make a guess. And it's based upon this idea that it takes some time for the information to get from one place to another. Yes?
You have 3 mu's as the indices. Is one of those supposed to be something else? I mean, muse. Shouldn't one of them be a-
Oh, you're asking how do we do the summation?
Yeah, one of those, the one on the A should be different than the one on the D.
Yeah,
If
I think
Ohanian
so.
got it
It
right.
should be different. So actually,
The A should have a new probably.
yeah. Thank you. Okay. So then, based upon this form, we're going to make the gas A mu, call it mu now, of T 3 vector x, right, is 1 over c integral. Here comes the tricky bit. That the potential at one particular place and time, right, depends upon what the currents were at another place and time, right, where the time goes in there. So I'm interested, I mean, this one's straightforward. I want to know what the field was. Oh, I should have. The dependence of the vector potential at one point on the current at another point. No, this remains the way it is, and this is one point in space and time, another point in space and time, where the relationship has got to be as the t prime is equal to t minus Okay, so there's a specific relationship between the current in one place and the field, the potentials at another place. Okay, it takes that much time for the information to get there. Okay, this is just based upon this idea that I put here, which I'll assert is true, but we want to actually demonstrate that it's true by making that supposition, saying that the relationship that works is the relationship between T prime, R prime, and, oops, R. Okay? So if this is true, then this is going to satisfy the wave equation, then we can solve for the fields. And what I'm going to tell you now is that in the work that we're going to do at the beginning of the next class, that will be shown to be plausible. I won't actually do all of the arithmetic, but I'll show you some of the tricks that are involved in order to in order to demonstrate that this is reasonable. Let me say that the primary trick that's involved is paying careful attention to real space gradients. So let's say that's a real space gradient of things like the primed time. Right? So the primed time is related to a real space vector. But we have to be very careful about how we do that when we go ahead and try to take del squared, for example, del squared of A. Now I'm going to have primed times in there and primed positions. I have to be careful about how I take the gradients and divergence and Laplacian in one set of vectors as related to the other. There's one really simple relationship that's nice, which is that at least we know that dt prime dt is equal to 1. All right? So that's actually stage 1, but then we actually have to, what we're going to do next time around is calculate that, where that is this, and we'll have to be careful about converting variables. Okay? So that's what we'll do next time. We're pretty much out of time for this.